So in the lecture series we have discussed about what is steam nozzles, what is the working principle, what is the application, and then we have discussed the derivation to find out the exit velocity of a steam nozzle. So in today's video we are going to discuss about the flow through the steam nozzles. Okay. So initially if you take a steam nozzle, so this is steam nozzle. So here the gases will be flowing inside or steam will be flowing inside and comes outside. Okay. So here already told that this is taken as inlet and this is exit. Okay. So initially we are assuming that the flow through this nozzle is isentropic. Flow through the nozzle is isentropic. So if the flow through the nozzle is isentropic, entropy is constant. Entropy is constant. S is equal to constant. So if you take the entropy at the inlet, it is taken as S1 and it is taken as S2 at the exit. So when the flow is isentropic, there is no heat transfer. Q is 0 into this system. So now what happens is, so based on this, S1 is equal to S2. S1 is equal to S2. So this is the condition for the flow through the steam nozzles. Okay. But what is the condition where it is used? Now let us take a small example. Now let us assume this steam is a dry saturated steam. Okay. Dry saturated steam which is entering inside with a particular pressure of P1. And then here the velocity is increased, and then here what happens is it becomes wet steam. It becomes wet steam. Now the properties of this dry steam at the inlet and the properties of the wet steam at the exit can be found with the help of this entropy constant. Okay. Now let us see this small graph. Okay. So if we take enthalpy at the y-axis, you are taking enthalpy at the y-axis and entropy at the x-axis. Entropy at the x-axis. So we are taking a particular pressure. So this pressure is P1. This pressure is P1, and here maybe another pressure P2. Okay. Another pressure P2. So initially, if you are knowing the pressure at the inlet, it is taken as P1. It is taken as P1. Okay. Let us assume this point is inlet. Based on the properties, we are fixing the point A. Okay. So when the flow process is isentropic, then what happens is the line will be straight. So this is B. This point is exit. Okay. Here when you calculate this, what happens is S1 is equal to S2. So this is the flow process between 1 and 2 in the Mollier chart. So correspondingly to the point A, we can calculate H1, and corresponding to B, we can calculate H2. That is enthalpy. Same way the pressure and then entropy is constant, that also can be calculated. Okay. So this is the condition for an isentropic flow. But in real cases, when the flow of steam takes place through the steam nozzles, in really what happens? Will the process will be isentropic or not? Okay. When the real time, when the gases, when the steam are flowing inside, the process will not be isentropic. The process will not be isentropic. That is, S1 will not be S2. S1 will not be S2. So what happens is, so likely there is a deviation like this. So now this is C. Now this is C. So C is the process where when the flow process not isentropic. Not isentropic. So here when the flow is isentropic, it is represented in A, B, whereas the flow when it is not isentropic is represented by A, C. So here what we are coming to know is when the steam flow through the nozzles, in real cases the process will not be isentropic. So here from this we can conclude here this is H1 minus H2. Now let us take this as H3. This is H1 minus or H2 dash. H2 dash. So here what happens is there is a drop in the enthalpy. There is a drop in the enthalpy. So when the flow is through a steam nozzle, so it is not isentropic, there is a drop in enthalpy. Okay. So we conclude that so in real cases when the flow through the nozzles, because of friction, okay, the process will not be isentropic, therefore S will not be constant. So this is the conclusion from our flow through the steam nozzles. Thank you.